Okay, so I'm destroyed Japan. I'll replace it. If you take any set of this form, which is in our Borel sigma field, saying the probability of AR equals R, the probability of the interval is just the width of the interval. That's a uniform distribution. So there's a beautiful extension theorem that says if I can define the probability on every interval, I can extend it, that probability, to the entire Borel sigma algebra. Okay, so that's again, that's a math course that we're not going to get into that. So there does exist an extension to anything here. Right? So you can, so there's some deep stuff we'll gloss over, and luckily we don't need it. It's not important to get into the details of why you can extend, just to find the probability measure on these simple sets. We can extend to anything in this huge collection of subsets. Great. All right. So, yeah. All right. Another one. Okay, here's the third example in chapter 1. So this is basically repeated binary trials, like repeated coin flips forever. Every day I flip a coin and I look to see if it's a heads or a tails or a 0 or 1. And I'd like to model that, all right? So you can play the same game as before and take omega identical to the possible, only that myopic view of the universe. All I care about is whether I see 0s or 1s every day after day. So you can see how unrealistic that is, that we only care about these coin flips, So. So it's all infinite sequences where the omega i's are either 0 or 1. All right. Again, I hate to repeat myself like this. The only reason I'm doing this is to practice the definitions. Again, if I cared about some infinite trials problem like this, I would not bother to define the sort of minimal omega. I would just say omega exists and not worry about it. Right? But there's some subtleties. What about F? The thing is that, do you see that this should have raised an alarm? We had trouble here with 0, 1, so therefore we should have trouble there. Because any real number has a binary expansion. So there's a one-to-one mapping between these guys and these guys. Basically, I can represent an omega here. Let's give these a name. Let's call this omega 3. So if you give me an omega over here, I can represent it as an infinite series like this, all right? And every real number between 0 and 1 can be represented as a as an infinite sequence. Right? And so if I couldn't take all subsets here, I can't take all subsets there. I'd be in trouble. And so what do? You play the same game as before. You say, well, what do I care about? You know, I'm mostly going to, you know, worry about a finite time horizon. And so you basically, you say, you know, start off with something simple. Okay, so they're not events yet because we're trying to design the probability space so they become events. And what would they be? So you can take any n. Now, two, three, four, five, six. Okay, so n equals 6. Here's an example. You know, so so for any n, I choose a binary vector, you know, and I want, and then I define an event EB. I should leave out those n's, but it's okay. Scribble out those n's. We don't need them. It's too confusing. All right. So these are things I would like to be able to define the probability of an event like that. Something that only involves the first n trials, all right? And so I just do the same thing as before. I just define F to be the smallest sigma algebra that contains these elementary guys. Okay, so they have to contain EB for every n and every sequence of zeros and ones. And by smallest, you know what I mean. I mean the intersection of all sigma algebras that contain all of these EBs, and that does exist. So that's what you would do. You know, I mean, you have to go through, and it's, you know, you'd have to do that. And so then, you know, here I said. The uniform distribution be a natural thing, you know, distribution on 0, 1, why not? What's a natural distribution on this? You know, how would you define P? Yeah, what I mean, like what's P of EB? So the fact is, again, there's an extension theorem. So if I can define P on all these elementary events, then I can define P on anything in the smallest sigma algebra that contains all the elementary events, right? And for this, well, it's already Bernoulli in the sense it's 0 and 1, but like a fair coin, it models what you're thinking. And so for P, you could take a fair, you know, independent coins. And that just means the probability of any one of these elementary events is, well, they're all indistinguishable. So probably if that was a half, a half, a half, a half, a half, a half. So it's 1/2 to the n. Okay. And again, so take a measure theory course and you can see that proves that extension theorem, okay? That's the only subtlety, right? I mean, I have things I care about. I would love to know the probability of this event, all right? And also I have a natural model which tells me what it is. And then it turns out there's a way of coming up with sigma algebra and extending the probability to anything in there, all right? Okay, but so this is important because it's like, this is our first stochastic process, you know? So this is an example of a stochastic process, and this is where limit theory comes in, and, you know, all sorts of things you've heard about law of large numbers and central limit theorems and large deviations, and you can look at the expected times to get some reward and all sorts of things. There are all sorts of things you can work with. There are all sorts of abstract events which are not of this form. Okay, and so let's play around with that a bit. And yeah, time flies. It's so funny, before, an hour ago I was joking that I'm going to cover about 100 definitions in 2 hours. And yeah, it's not like that. And slow me down, okay? I mean, you know, I've got some great questions, so keep it up. So what do I want to say here? So if I just define like x n of omega to be equal to omega n, you know, that's the value of the nth trial, you know. You wouldn't want to say omega n is the random variable. It would just be a terrible notational clash. So even though I think Bruce Hayek does that in the book, but just let's keep the notation. A random variable is a function on capital omega. We've taken real valued random variables so far. And in this case, let's just define xn of omega to be omega n, so just the nth entry. We know that that's going to be in F. I mean, it's a random variable. It's a random variable with respect to this sigma algebra, and we're not going to prove that. But basically, what I mean by that is that the event, the set of omega, such that xn of omega equals r, is an element of F for any real value r. Or I should say less than or equal to. That's how it was defined before. Let's remember that's the definition of a random variable. We have to have this condition that, I remember I said random variables are functions. Well, there's one more condition. If I look at these sub-level sets, they have to be an F for any real valued r. That's the definition of a random variable, you know. And it's because you'd like to know the probability of these events. All right. Now, xn of omega just takes on two values, 0, 1. So this set is the empty set until r is 0. And then it becomes what? When r is between 0 and 1, it's just, you know, whether or not omega n equals 0, 1. I mean, let's write it down. Okay, so probably that omega n is negative is the empty set. I mean, the event that this thing is negative is the empty set. When r is is greater equal to 0 but less than 1, it's just 1. I mean, not 1. It's definitely easy to get confused in all this. So if r is between 0 and 1, this is a set of all strings whose nth coordinate is equal to 0, 0, 0. Turn off the mic. All right. Ask me, not your neighbor. What?
No, I think
why is it omega is empty?
Oh God! It's just that I'm getting myself flustered because I wasn't going to do this. Thank you. No, you scream at me, not your neighbor. No, it's easy to make mistakes when you're trying to rush through it, something so simple. That's the trouble. It's something that I didn't want to say that's so elementary, and then I'm rushing through it. I shouldn't do that. I should go through slowly. So slow me down. But if you just look at this, x can never be negative. So that's why we get the empty set, not everything. And if r is between 0 and 1, the only way this is possible is if the nth entry is actually equal to 0, because xn only can take on two values, 0, 1. And if r is greater or equal to 1, what happens? What's the event that xn omega is less than or equal to 20? You know? Thank you. Yeah. All right. So omega is in F, the empty set's in F, and that thing there is in F because it can be represented as intersections of these elementary events. All right. So that's that. So the kind of things you might be interested in is what? Like these hitting times. Now I'm using some jargon which I'll define later. Stopping time has a very crisp, important definition. I'm not going to define it now, but I'll give you an example. So let's see. Okay, one. Okay, so this is like the first time I get a heads, you know. So basically, somebody gives me $100 when I get a heads, and they take away money when I get a tails, you know. So I really care about the first time that I get my reward, all right? Now this is something that really depends on the whole sequence. So tau is a random variable. It's a random variable that takes some values in the integers, you know, because it's a, it takes the value 1. If I got a head, it's in the first roll, and so forth. And it's not, you know, I mean, it's, when I look at events associated to tau, I have to be really careful to set things up so I can write them in terms of these simple events. And so what are the kind of things you'd like to ask? So here's a tough one. You know, you look at something like this. What's an event that the time at which I got a heads is an even number? You know, I don't know why you'd care about that, but you know, maybe you do. Maybe this would come up in some problem. You would like to know: is this an event? Is it in this smallest sigma algebra? The way you check that is if you could write it in terms of these elementary events, and you'd like to know its probability. And so somebody tell me how you go about, especially working out probability V. You know, if you just try to hit this directly, you're dead. You know, we got to use our axioms. So we only have, in terms of P, there's only 3 axioms. You know, we can use it probably, the fact that P of omega is 1, I don't think that's going to be very useful. And we can use the fact that, you know, I mean, there's another axiom in there, relating something. There's only one axiom that's important. Go look at your notes. The sum, yeah. So if we want to compute P of E, we're going to have to be able to write E as a union, a disjoint union. And so So how are we going to do this? So let's introduce some more notation. Let's let EK be equal to the set of omega such that tau of omega equals k. And what is that? It's the set of omega. What is it? It's the set of omega such that what? It means that the what?
Such that n is greater than or equal to k.
Where's
The
n?
minimum n.
No. Think about in words. Tau is the first time I got a 1. And so what if that for this for any k? So what does it mean to say that tau of omega equals k, given that just that language?
First k minus 1s are 0s.
Yep.
And then the kth one is 1.
That's that. You know what I mean? It's just, and so it actually is exactly one of our elementary events. This is actually equal to EB for some B. You know, some P, not some B. And so we know that, E. I know how we'll get to tau in a second. So we know what P of EK is. We know that it's, basically this is this fair uniform coin, but we're taking that fair model, and so it's just equal to 2 to the minus k. Right. And so what about our event that we care about over here? Can we express that in terms of these guys? Yes. Absolutely. Because we only care about the k's here that are even. That's one way to say it. So basically, that's it. And these guys are all mutually exclusive, they're disjoint. And so I can write down the P of E is sum of the probabilities. All right, so this is only because it's a disjoint union, of course, but it's easy to make mistakes there. And then you have to go through and say, what the hell is that? And so it looks like it's the sum of 1/4 to the n. It makes it easier. And then we all know that's, it's a geometric series. So it's 1/4 over 1 minus 1/4. And so you multiply the top by 4, and you get 4 minus 1 is 3. So, all right. So you start with something that looks hard. The probability that the first time I get a heads is even. That time is even, and it turns out to just be trivial if you set it up the right way. And the thing is that often you come up with problems where if you set up the right way, it's that trivial, and if you set up a different way, it's impossible. So that's the curse of this field. Okay. All right. What do we do? So it's been an hour, and I'm starting to see people people yawning. What? Yeah. Yeah.
So that immediately implies that the probability of all odds is 2/3.
Yeah, absolutely.
All odds.
Absolutely. So it's much more likely to get an odd time than an even, and that's only because of the first. Because of the first roll. Yeah, because 1 is odd. Yeah. Yeah. But let's just keep going. So the whole course won't be like this. So the way the course goes is I'm torturing you with a lot of these basic definitions, which you have to practice sort of a common language. So when I say a random variable, you know what I mean. When I write down the probability that x is less than 3, you know what I mean. I really mean this is equal to the probability of the set of omega such that x of omega is less than or equal to 3, or less than 3. Whatever. I mean, we need a common language. And as the course goes on, and we all have the same language, the course will become much more algorithmic, and we'll have all sorts of fun toys to play with. But we definitely need this background. We're dead without it. Let's just keep going. I mean, so what's been under the rug all this time? Right here, I was talking about an independent trial, so we should define independence. And somebody remind me what that means. What is it? What's independence? I can hear somebody mumbling it. All right. Okay, so you got two A and B's that are events, so you can define the probabilities. They're independent if the probability of the intersection is the product of the probabilities. That sounds so boring and mundane, it's ridiculous. It's only interesting when you talk about stochastic processes. So, X and Y are independent. So I've just written something without any explanation. What do I mean? So basically you've got this from baby probability, undergraduate probability, and then you have independence of random variables. And what do I mean? What's AR and BS besides BS?
Pretty much the domain of your random variable?
Nah. So remember the definition of a random variable is right there, that's an F for any R. So that's what it means for the events, they're events, yeah. So I have a primary definition here about definition of independence in terms of events, and from that you get a definition of independence of random variables. The AR and the BS's are just like these guys. So AR, you take AR to be equal to the set of omega such that X of omega is less than or equal to R, and BS equals the set of omega such that Y of omega is less than or equal to S for all real S and R. Okay, so that's what we mean. And so this is much deeper and important. This definition is only imposed so we can talk about independence of random variables. Right? Really, that's it. And so it's a modeling tool. Basically we assume that sequences are independent is a simplifying assumption in models. When we get to these Markovian models we'll talk about, so a lot of you haven't seen them before, it's just a modeling assumption to make things simple. That's really it. So what do we do with this? Where is it? Well, we do all sorts of things. I don't want to do that yet. There's too many things to say. 1 second. Oh yeah, no, I know what to do. No, to be continued. Let's do something much more pressing. I just bring this up here because I was talking about independence of the sequence here, and there's a formal definition. something much more pressing. So you have this abstract world and you go back to reality through a CDF, a cumulative distribution function. So give me a random variable, there's a CDF. And that is denoted f of c for any real number c is the probability that x is less than or equal to c, which in the previous notation is the probability of AC. Okay, so there's a function. So what can you tell me about it right away? As I make c bigger, this set gets bigger and bigger and bigger, so it's non-decreasing. You know, and we can get all sorts of other properties as well. All right. Oh geez, did I skip too far? I think I did. 1 second. I did. I skipped a whole bunch of things I wanted to say. Doesn't matter. Let's put them under the rug. To be shown. Yeah, it's much better to jump to applications and explain the results later. So way back here, it's near 0, then it goes along, and I said it's non-decreasing. It's really hard to see that, but it's non-decreasing, and it can take a jump. You know, but it takes a jump with a solid line there and an open line there. And then over here is an asymptote, which is 1, and this asymptote here is 0. Okay? So it's non-decreasing, it can take jumps, but it's right continuous, and it converges to 1. Okay, so the right continuity and the fact that it converges to 1 are all really important consequences of that union result. The fact that probability of a disjoint union is the sum of the probabilities. And so it takes a bit of muscle to do that. And we'll just do that next time, briefly. You know, let's play around with this some more in other ways. So when Neil defined expectation for you, he defined a simple random variable. Did he? On Tuesday?
Yes.
All right. So if you have a simple random variable, then there's somebody's given you a set, say n different elements, and x omega is in that set for any omega. For example, for the roll of a dice, n is 6. This is 1, 2, 3, 4, 5, 6. You know. All right. For the Bernoulli thing we saw before, there's two values 0, 1. N is 2. And this is 0, 1. Right. And so what does it look like in that case? So you just basically mark on the c-axis these locations. To make it easy myself, n equals 4. So there's 4 locations here. And you look at any c to the left of x1, the probability of being less than or equal to that value is 0. All right. So basically you have this thing staying at 0, and there's an open thing there and it jumps up because I said it's right continuous, and then it stays constant. And what is that jump? The probability of exactly x1. And then it jumps again at x2. Possibly, I didn't say the probability of being at x2 is positive. It might be 0. It might be the probability that it hits x2 is 0. But let's say they're all positive. And it just keeps doing that. And then it jumps up. The probability of being less than or equal to x4 is what? I put these in order. What's the probability of being less than or equal to x4 if they're in order? 1, yeah. So it jumped up here, and now it's less than or equal to something less than x4. So it will jump to 1 there. Okay, so this little pk is a probability that x equals little xk. No, that's what I'm saying. All right, so discrete random variables have jumps, continuous random variables have a density, it's continuous, and blah, blah, blah. So Neil